All right, next up we have Harley Katz from the University of Chicago, and we're going to leave observations and go over to theory.
Oh.
No, I'll give some of both. So I'll do about 10 minutes of theory and 10 minutes of observation. So feel free to fall asleep during which section you talk about. But I'm going to be focusing, on the highest redshift. But I'm excited to be able to talk about observations. And the reason why I am so excited about observations is because there genuinely has been a revolution in spectroscopy. I think it's worth showing that this is the highest spectroscopically confirmed galaxy using the GRISM on Hubble. You can barely make out the fact that there's a Lyman break here. But then, of course, if you look at the same exact system with James Webb, I mean, this is the third time we've shown the same spectrum, and we're only 5 talks in, which tells you how good it actually is. It's really quite remarkable. You see, beautiful Lyman break and all these emission lines. Even getting the redshift was difficult with a Hubble system. Okay. And the reason why we're so excited about this is because these spectra contain a huge amount of information about galaxy formation. And it really genuinely is a key theoretical challenge about how you extract this information. So to give you a few examples, this is one of the first near-spec observations of a redshift 6 and above galaxy. This is in the ERO data. You have H beta, which tells you something about star formation rate. You have a combination of Balmer lines, which tells you about dust. If you combine different ionization states of oxygen, you learn about the ionization parameter. If you combine metal lines like oxygen with Balmer lines, you can learn about metallicity. And then if you try to fit the entire shape of the continuum, you can learn things about stellar mass. Now, you don't have to do this in emission. If you look on the right, you see a Muse galaxy. You see these beautiful absorption lines. And this is going to be telling you about some of the gas that's surrounding the galaxies, right? The photons have to flow through this gas. You can learn things about, the metallicities of outflows, velocities of outflows, and general properties of outflows. So over the next 5 to 10 years, we're going to be learning a ton about the interstellar medium at redshifts greater than 10, and probably CGM and outflow properties around redshifts greater than 5. Okay? And this is really where simulations come in, because simulations are an ideal tool that we can use to help interpret these types of observations. Now, you can ask, how do we currently model emission lines? Now, I was here about 6 years ago. This is almost the exact same slide I showed 6 years ago. You take a very high-resolution cosmological simulation of a redshift 10 galaxy. You include radiative transfer and things like that. So for every single cell in the simulation, we know density, temperature, metallicity, radiation field, which is pretty much all you need to know in order to predict the emission lines. You run it through your black box of post-processing, and you can produce these beautiful emission line maps. Now, if I zoom in on what that black box is, this is the exact slide I showed 6 years ago. It's an incredibly convoluted process that includes a huge amount of assumptions. And this is really the key limiting factor, is despite the fact that we have these amazing simulations, actually converting them into the observations is a really difficult thing to do, and it's almost model and assumption dependent. That doesn't mean we can't learn anything. Of course we can. It's just a hard process. And in those last 6 years, what we've done is we've applied the same technique to the Sphinx 20 simulation, which is an extremely large cosmological radiation hydrodynamic simulation. For every single snapshot, it has about 30,000 galaxies. We post-process, all of them, or as many as we could, and you can produce these, beautiful maps that are designed to, look like what James Webb would see, although we haven't applied the PSF or else it would wash out my beautiful. Nevertheless, we also produce spectra. Here's just an example of a single galaxy. You see beautiful Balmer break, all these different emission lines, and instead of just getting it for one line of sight, the same galaxy can be viewed at many different viewing angles. Those are these different blue lines, and you can see how the same galaxy with the same underlying physical properties looks very different depending on the angle that you view it at. Okay? And what have we learned from this? The goal isn't to just mock it. We're trying to extract some physics. There's a lot of ways we can use these simulations to remove physical biases in interpreting observations. Here's a really cool example with metallicity. On the x-axis is the true metallicity of our galaxies. On the y-axis is the value predicted by observers using what's called the direct method. This is the gold standard of metallicity measurements. If they were correct, they'd all fall on the dashed red line, which is the one-to-one relation. And you can see that metallicity is systematically underpredicted using this method. Okay, and you can ask why that is. I can discuss that after the fact. But if you then sort of propagate this into the mass-metallicity relation, this is the low mass n, so you have stellar mass versus metallicity. The black points in line is what you'd expect using sort of the uncalibrated sort of standard direct method. And if you take into account this bias, you see not only the normalization, but the shape also changes. You can apply the same thing to star formation rate. On the x-axis is H alpha luminosity, the y-axis is star formation rate. The typical Kennecott calibration is this magenta line, which you see does not go through our simulated data. That's not too surprising. We use a different single stellar population. We use BPAS, which emits more ionizing photons, which shifts the relation to the right. That's what's given by these red lines, which you can see do a little bit better. But what ends up happening is the cyan line, which is actually the fit to our data, actually interpolates between these different red lines because there is a mass metallicity relation. Lower metallicity galaxies emit more ionizing photons. Okay? So that's why you get these offsets from Kennecott. Now there's an even more interesting effect. If you look at the residuals and you compare them to stellar age, you see that the predicted versus the true SFR actually varies depending on the stellar age. And the reason why is because in all of these calibrations, we're assuming that the star formation rate is constant over 100 million years. At redshifts of around 6 to 10, there hasn't been 100 million years for the galaxy star formation rate to remain constant. So if we want to be precise with this, we're going to have to do a little bit better. You can play the same thing with psi-ion, which is an important parameter for reionization. Again, it does not fall in the one-to-one relation. Here, the biggest issue is dust. If you take systems with very low dust content, you can see that we can get. Of course, this is an old method. We've been doing this for about a decade, and I really think it's time we start changing how we model and mock observations from simulations. So we've been developing this brand new code called Ramsey's RTZ, and essentially what it does is it takes all of the physics that's in these post-processing codes. It tries to measure the level populations and ion properties. So all of the physics that controls ion and molecular properties, ionization, recombination, charge exchange, and all of the different processes that control gas temperature, heating processes, cooling processes, processes associated with galaxy formation. We can now plug all of these into a 3D cosmological setting and run it fully in non-equilibrium. What we do is we calibrate this so that we reproduce the Milky Way's ISM. So if you just look at temperature versus density, and you look at this light green line, these are the calibrations from the Milky Way ISM, and then we allow these sort of calibrations to evolve to lower metallicities. If you go all the way down to 10 to the minus 5 solar, you see we don't even have a cooling instability anymore, and the ISM is actually no longer even multi, which is quite an interesting concept. So what can you do with this type of code? So this is a simple rendition of what a cloudy model looks like. You put a source inside, a spherical region. You let the radiation emit. You let it ionize, produce these different zones of ionization. You can then measure line luminosities versus, some input parameter. In this case, is gas density. I forget, one of these dotted lines is cloudy and the other one is our version. But the point is that in these very simple setups, our code is almost identical to cloudy. However, you can do the next dumbest thing and say, what if our H2 region is not a sphere? It might look something like this. So this is where we take a cloud and we just stir it up using what's considered a natural mode of compressive to turbulent energy. We put a source right at the center. So the source is sitting right in here. Here you're looking at the gas, a 3D gas density slice, the gas column density. Here's the temperature of the gas. You can see it's got this weird butterfly shape. You can look at oxygen 2 integrated or a slice of oxygen 2. You can see that the oxygen 2 forms right at the edge of the surrounding sphere, or oxygen 3, which is filling the gas. You can then remeasure the emission lines in this setting, and you can compare to the simple model, the simple spherical model. So on the x-axis here is different metallicities. On the y-axis is the line ratio of things like O3 to H beta, N2 to H alpha, or O32. The stars represent the spherical models, and these cyan points with error bars represent 10 different realizations of what we get from these turbulent models. Okay, and I'm sure Yifei will talk a lot about this, later in the week. But the point that you should take away from this is that all you have to do is change the geometry and know physics, and you can get wildly different emission line ratios. Of course, you don't have to stop here. This is a very simple exercise. We can now run this in a full cosmological galaxy formation setting. So this is a simulation we're calling Megatron. It's an early forming Milky Way mass galaxy. It's got population 3 and pop 2 star formation, about 1 parsec resolution. When this turns on, it's got 8 bins of radiation to transfer all of the chemistry you could ever want. And what's really cool about this is that this movie that you're looking at on the right, so the purple is gas density, but the white is H beta emission. This is being calculated on the fly in the simulation in non-equilibrium. The reason why it's expanding out is you're actually seeing the universe reionize. So these ionized bubbles are emitting an H beta. The yellow, we start at 0 metallicity. This is oxygen 3 emission. You can actually see the metals get pumped out into the intergalactic medium. As you see these flickering going on, these are these catastrophic star formation events that's going on in these early galaxies. So So now without post-processing, we can actually predict a map of what an observer might see if they had basically infinite integration, which I think is quite cool. Okay, so some of the first results coming out of Megatron, which I think are very exciting, is these are actually coming out of the calibration simulations. This is an example where we just take the same simulation of the same galaxy and we just change the star formation. So we do nothing about the major physics. It's just changing whether or not stars form with a turbulent mode or various different density models. And if you look at the stellar mass formed versus the age of the universe, these different star formation algorithms are pretty much indistinguishable. Okay? They form the same amount of stars. But if you look into the interstellar medium, this is the oxygen 3-2 ratio, and this is the probability distribution function of that line ratio, what you see is that the star formation criteria actually really strongly impacts the O32 line ratio. So our current ways of sort of calibrating feedback in star formation algorithms using stellar mass, halo mass relations, et cetera, those don't differentiate here in stellar mass, but if you look deep into the ISM, the properties are wildly different. So I really feel that the ISM is going to be a new way to constrain our galaxy. Okay? That's the end of the simulations talk, so theorists, you can go to sleep now. Observers, time to wake up. Simulations aren't perfect. I can now say that because the observers are paying attention. And as we've heard a million times, there seem to be more bright galaxies at high redshift than expected. Okay? And this is just a plot from Steve Finkelstein's work. If you look at the cumulative surface density of galaxies above some magnitude, greater than some redshift, the observations are coming in here, and most of the pre-James Webb models tend to be well below this. And as you've heard from UCI and many others, you'll hear a lot about this later today and tomorrow. There's been many proposed solutions, whether it be increased star formation efficiency, large fluctuations in UV luminosity due to bursty star formation, changes in mass to light ratio, for example, a top-heavy IMF, or if you're particularly ambitious, you might even claim lambda CDM stroke. Now, I think these are all great, and the true result probably lies somewhere in between almost all of these. Perhaps I wouldn't throw my weight behind this one, but maybe all of these other ones. However, I think there's one important component that tends to be missing from these analyses, and that's that gas emission can be extremely strong in these galaxies. Okay, and so to give you an example of what that means, on the x-axis here is wavelength or time. Here you're looking at 3 galaxies from the Sphinx simulation, one with a relatively smooth star formation rate, one with kind of a cyclic bursty model, and then one that's extremely bursty. Now the cyan line is the stellar emission, and the pink line is the gaseous emission. And you can see as star formation goes burstier and burstier, the gas emission really starts to play a role. So what is this gas emission? Okay, here's a sort of deconstructed spectrum of a galaxy. This is the stellar continuum. It's more or less a power law with this, bump, this Balmer break. You have free emission from, ionized hydrogen and electrons interacting. This tends to be subdominant. You have the free bound emission, which comes from electrons just recombining direct into certain states. You see it's got this clear ladder type morphology that we're gonna talk about a little bit more. You have the 2 photon emission, which is a 2s to 1s transition in hydrogen. You can see it's more or less a power law, but the key feature is a very strong downturn in the UV just near Lyman alpha. And finally, of course, you have the nebular emission lines, which we all know and love, and that's where we get all of our ISM pictures. Okay? And James Webb usually probes in sort of this regime at very high redshift. Now, you can ask, how much does the nebular emission actually contribute to the UV and optics? I've just taken 4 off-the-shelf SPS models, Starburst 99, DPAS, Rougeot and Charlot, and FSPS. As a function of stellar age, here you're looking at the fraction of the emission at either the UV in magenta or the optical in blue that comes from the gas and not the stars. And you can see it goes down with time as the ionizing luminosity drops, but at very young stellar ages, for off-the-shelf SPS models, this can represent about half the total UV luminosity. Okay? And if you apply this to real star formation histories, there's a tail in this distribution where you do nothing else, you don't change any physics, you just add the gas emission, and your UV luminosity is offset by 0.7 magnitude. Okay, that's really quite large. It doesn't explain the whole tension, but it explains, part of it, which I think is an important component. Now you can ask, what would you need for the gas emission to explain the rest of this tension? Well, one way to do it, there's a few different ways, but I'll focus on one. If stars are hotter or more massive, so here I'm just plotting the stellar temperature on the x-axis versus that same quantity. Okay? If you look at the solid lines, this is the UV emission. It depends a bit on gas density, and I can can talk about the physics about why that occurs a bit after if you're interested. But you can see for these hot stars, about 80% of the total UV emission is actually coming from the gas and not the stellar emission. And so if there genuinely are hot stars in these high redshift galaxies, that could very fully explain the UV. Okay? Now, how do you test this? Well, there's three key observables to identify hot and massive stars. The first one is UV slopes become redder. This is a very well-known piece of physics, okay? On the x-axis is stellar age, the y-axis is beta slope. The intrinsic stellar SEVs have beta slopes of around -3, but as soon as you add in the gas emission, it jumps up to about -2.5. Now, if you look at the hotter stars model, UV slopes can go to -2 or even -1. And this is actually a really key thing to think about. If you're looking for population 3 stars that have stellar temperatures of around 100,000 Kelvin, you should not be looking for blue galaxies, you should be looking for red galaxies. They can go as red as a UV slope of -1. So we might simply have been looking in the wrong. The second is the ionizing photon production efficiencies increase. So if you look at hotter star models, on the x-axis is the intrinsic psi ion. A typical SPS model gives you a psi ion of around 26, but the hot star models extend well past it. Unfortunately, this is not an observable feature of the galaxy, and the reason why is because we compare an H beta line or an H alpha line to the UV emission, but this also pumps up the UV emission, so you're basically comparing gas to gas at that point. So no matter what you do, you can pump this as far as you want in psi ion. You'll basically never observe a psi ion above 20. So in fact, really, if you observe a psi ion above around 25.7 or 25.8, that's where you can start being worried about maybe there's hot stars. The final thing is the 2-photon emission has a very, characteristic signature that there's a downturn in the UV. When we see UV downturns, as Mathilde just showed you, we usually think they're DLAs. Okay? So when we see these UV downturns, people just fit it as a DLA, and depending on the stellar temperature, these DLAs can go up to easily 10 to the 20. So if you see very, very high column density DLAs, and for example, Lyman alpha emission occurring simultaneously, that might be an indication that it's not a DLA, it's in fact a nebula. Okay, so how do we test this? Well, I've gone through about 14,000 spectra by eye to try to find signatures of this physics. I found about 150 galaxies. Here's just a sample of 20 of my favorites. Here you see that jump feature that I was telling you about. This is the Balmer jump. And then you see many of these galaxies have a very strong UV downturn. You can take all these galaxies and stack them up. It looks a lot better. Now you can really see the gas emission popping out. The gas emission is clearly dominating at these wavelengths. And you can see in the stack there is a clear feature of a downturn, which would be indicative of Jupiter. In fact, not all of these host very hot and massive stars, but there are 3 very peculiar galaxies that we found. Here are the 3 galaxies. The spectra are just overlaid over each other. And the key features I want you to look at are it has a very flat UV slope. As you can see here, it's a slope of about -2, which is much, much, much flatter than you'd expect from normal star formation. It has a clear Balmer jump, so we know the gas emission is important. And it has a very strong UV downturn and very, very strong Lyman alpha. Okay, so you have to ask yourself, if there is a DLA in the system, why is the Lyman alpha escape fraction 30 to 50%? When the DLA would be among the highest DLA columns we've ever seen. Even more importantly, if you look at psi ion, in particular for this galaxy, the psi ion is above 26, which is higher than you can get from any SPS model in observational setting. It's remarkably high. If you also look at the H alpha equivalent width at 3,300, it's one of the highest H alpha equivalent width galaxies in the world. So these are 3 candidate galaxies for hosting these hot masses. In the interest of, I got 2 minutes, I'm going to skip gravitational lensing, but we can talk about that. The point of this was to look at very high redshift. Is there any evidence that these extremely high redshift galaxies host these hot massive stars? Well, unfortunately, you've seen some of the spectra. There's not too much we know about them other than their UV slopes and the shape of the Lyman ray. So if you just look at the UV slopes, they tend to sort of be in the region where the gas emission is clearly very important, but some of them are inexplicably high in this pink regime, which are higher than we expect from these standard SPS. So these are the key galaxies right here that could be candidates for hosting very hot masses. And these are all galaxies above redshift. Now, one thing you can do is you compare the UV slope to D Lyman alpha, which essentially tells you how strong that downturn is, okay? The normal SPS models, so normal stellar evolution, predicts sort of in this regime, which is consistent with many of them. But of course, you have these two whopping outliers. And if you look at the prediction from the hot star models, and these two red points are two of the galaxies I showed you on the previous slide, they're almost in perfect agreement. These are two very strong candidates for hosting these extreme hot massive stars. So to conclude, these high quality, high redshift galaxy spectra are really transforming our knowledge of the early universe. This is a key theoretical challenge, okay, which I think simulations can help. For this reason, we've developed this Ramsey's RTD code that can do all of this stuff you're using Cloudy for photoionization models and processing. We can now run it fully on the fly in non-equilibrium. Some of the stuff that's coming out of it is, geometry and turbulence matters. There's clear biases in how we do parameter estimation, particularly metallicity. This is really where simulations can step in and play a role. Also, ISM observables can be used that can actually constrain the underlying physical models in the simulation. The nebular continuum, this gas emission, is potentially a very important source for UV luminosity at high redshift. It might not explain the whole tension, but it can significantly reduce it, okay? Which I think can really help. However, if there are hot and massive stars in these early universe, this would more than explain this tension. So I'll jump back to theory and just leave you with a movie of now the Megatron simulation at redshift. Thank you.
All right, we have time for a couple questions. All right, we're going to go back there to Joe.
Great stuff, Harley. Thank you. On the first movie you showed, there was you had some color coding by line emission, I think.
Yes.
What were the filaments? It was sort of a magenta.
Oh, that was gas density. So that wasn't actual line emission. That was sort of showing you where the gas was. Yeah.
Great, thank you.
Okay. I saw Mark first.
So, counter to expectations, I'm going to ask about the observational part of the talk. So it seems like there's another potential signature of the presence of very hot stars you could look for, which is the helium-2 recombination lines. And so, I mean, there is this population of galaxies that have very high helium-2 to H-beta ratios. Do these galaxies you're looking at, what is the overlap between that class of galaxy and the ones that have these funky UV spectral slopes and other features?
I'll counter your point by saying we actually have no idea what the helium-2 emission should be. So for a typical population 3 star, you expect it to be, if you just take a 10 to the 5 Kelvin black body, the helium-2 equivalent width can jump to, like 50, 80 angstroms or something silly. The problem is you're in the region of the SED where it's the highest uncertainty. So if you look at, for example, the massive hot star models at like a 10th solar metallicity to 0 metallicity, anywhere in between that, you can go to basically no helium emission to tons of helium emission. So because the stellar atmospheres are so highly uncertain, particularly at wavelengths below 200 angstroms, we don't know what the helium should be coming out of. So at low redshift, there is some indication. For example, Grace Olivier had this beautiful paper using, I think it was classic galaxies, if I'm wrong, where they showed that a hot black body would boost the helium-2 and would be in agreement with sort of, what I'm saying here. But again, it's the black body emission is the real underlying problem, is we don't know what the stellar atmosphere is doing. So you can get any, unfortunately.
All right, and one last question for Harley.
Can you say more about O32? You showed a neat relation and were suggesting, I think, that it could differentiate the star formation histories? Or I may have missed the point there, but it was a tight relationship.
Yeah, so what's going on here is basically these different algorithms are just different ways people in simulations try to form stars. So some people use some turbulence model that's given by this black line. Some people use, once the gas hits a certain density, they use, 10% efficiency or 100% efficiency, or they change the density threshold, okay? And what happens is because, the O2 line is very sensitive to the gas density, and the O3-2 ratio together is sensitive to ionization parameter. This controls basically how clustered the star formation is and the density of the gas around the stars. And so it turns out that ratio is a really good way to differentiate these sort of subgrid algorithms, which we kind of don't think too much about, but it turns out that the ISM is an extremely strong program, which I think is cool, right? It's just another tool we have now in order to improve.
Okay. All right. Great. Let's have Harley again.